This video, it it continues the discussion about experimental phenomena and people's efforts at modeling the atom. So this is material in chapter 6 of your book, and questions and problems that are associated with stuff that's going to unfold in this video is this list here. So questions 5, 6, 9, and 17, and then I guess a pretty large list of problems. There's 6 problems, 15, 21, 24, 26, 27, 31. These are listed on Canvas as well in your course website. So in continuing the discussion, the next section in the chapter 6, starts off or continues with line spectra. And I'm going to appeal to your memories because I'm pretty sure that everybody in the lecture is also in the lab. So there is a device that we learned to use called a spectroscope, and it was a device where you could see or scope the spectrum, and in particular we're talking about light. Now the problem that we faced when we were looking at the spectroscope, although it wasn't really a problem, but it's actually a limitation. The spectroscope that we used was limited to the sensitivity of our eyes. So there's a couple of sensitivities. There's a sensitivity of brightness, but also, even more, a sensitivity to only visible light. So the interesting thing to point out is atoms, like we're talking about modeling atoms and experimental phenomena associated with atoms. So the light that is emitted, so we're talking emission of light from single atoms, not molecular structures or crystal structures, although those things also emit light. But we're talking like individual atom systems, so individual atoms emitting light, and they can emit light in the visible wavelengths, but they can also emit light in ultraviolet and also infrared. Probably largely they emit light in the low energy, so infrared, maybe far infrared. Well, actually, I shouldn't say that. Anyhow, when we were using the spectroscope, we were using our eyeball as the sensitive instrument. And we could see visible light, so we could see the visible light part of the emission spectrum. So these line spectra, and in particular for hydrogen atoms, the line spectra for hydrogen atoms was kind of like an early stack of experimental data that people tried to develop models for. And there is a famous person named Balmer who developed a model. And the truth is I think that it's appropriate It is a phenomenological model. It's based on just the phenomenon. There's so this model, it gets written this way. So the wavelength of the color of the emission of an atom comes in a list, and the list is defined this way. So you could say that the wavelength of the nth color is equal to some what's called limit wavelength. And I'm going to add to this idea of the limit wavelength, multiplying the number n squared divided by n squared minus n sub 0 squared, like this. For Balmer, this little n sub 0 takes the value 2, so there's a little 4 being subtracted there. And this limit wavelength is a limit wavelength that's labeled by that n sub 0. So the thing about n is integer, and n is bigger than n naught. So n is at least n naught plus 1, for example. If n could have the same value as n naught, then the lower part would be 0, and then we get an infinite wavelength. Which honestly sort of makes sense. But also, like, if n was smaller than n naught, then I'd be talking about negative wavelengths. That doesn't make any sense, right? There's no negative wavelength. But anyways, this was an early model. It's a phenomenological model in the sense that this is a function, sort of comes from nowhere in terms of first principles of physics. Nowhere in physics, it just matches data reasonably well, or very well. But the point is, though, is that this model here, it looks like it should come from some physics. So the question becomes, how can we predict this kind of model, right? That's the physics question. How do we predict this from what we might call first principles, or basic, aka basic physics? So this is the million-dollar question. Here is a stepping stone on the way, because somebody really smart noticed that this kind of construction with integers gives a map of the right answer. It gives the list of wavelengths seen in the emission spectrum, and it does so completely. It doesn't skip any. It doesn't add any that you don't see. Yeah, so it's predictive, but nobody knows where it comes from. So more work needs to be done. Let me add, actually, at the bottom, there's something else that's mentioned in your book in about the same place, called the Ritz combination principle. And it is a combination principle of frequencies. And there's something really simple that happens. It's also somewhat phenomenological. It's just a pattern that this person, Ritz, noticed. And so this pattern ought to be predictable from some basic physics, is the idea. So you know that the story largely is these first principles, or basic ideas in physics. The first principles need to start from something completely new called quantum mechanics, or quantum physics. But remember, this is the story of the development of everybody's idea that something is wrong with all of their classic basic first principles, and something completely new is going to show up. Namely, it's the Schrödinger equation, and de Broglie wavelength, and probability, and all that stuff. That's what's coming. But yeah. So let's see. So a model that has a lot of success predicting phenomena like emission spectra and the Ritz combo principle. So the model that has a lot of success, so successful predicting phenomena like emission spectra and the Ritz combo principle, is the Bohr model of the atom. And what's really interesting is if you look at, here's one of the first principles, you might say. And this one, let me put a question mark. Why? So why would this person Bohr, Niels Bohr, claim that as a first principle, angular momentum, oops, I'm misspelling everything right now. Angular momentum is quantized. What can this mean? Anyways, if he makes this sort of judgment call, but then adds in another first principle, which is honestly just Coulomb's law, and another first principle of energy conservation, where light can deliver energy to and from atoms, right? So light is a phenomenon that includes a wavelength and a frequency. So what's really cool is Bohr says, well, atoms are made out of electric charge, and this is how we understand force associated with electric charge. Energy conservation is another rule, and Coulomb's electric field is a so-called conservative. You can make a potential energy and blah, 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 but if you include in this energy statement about the energy of an atom that light can bring in energy and take energy away, if you take these two first principles, which are really basic physics, and then you add this like crazy choice, angular momentum is quantized, out pops all the series, so Balmer series plus for the hydrogen atom spectrum, and Ritz, the Ritz combination principle. So this thing right here is, it's an informed guess. It's like a why not. He's a theorist, and why the hell not? If I was in his position, I wouldn't have been brave enough, quite honestly. I wouldn't have been creative enough. I wouldn't have tried it anyways. Maybe you could take this as a student as sort of an exciting, I get to do anything I want. I just need to make sure that it could be important, you know, or I need to follow through on things until I can decide that it's not the right direction to go, or is not going to be an important direction to go. But yeah, so this took a leap of creativity that's pretty extraordinary for Bohr and some of his collaborators to do, his graduate students, his, you know, people he collaborated with in science. Anyhow, so he can predict this, and so this is a first principles build-up for a prediction of some, what I referred to as phenomenological modeling efforts. Yeah, so he could literally predict this formula based on these kinds of ideas. Two of which aren't novel, but the third is what the hell were you thinking? That's really cool.